Hello everyone. Welcome to our session on interpretability of machine learning models. In today's session, we will try and understand the following issues. What exactly is interpretability? Why is it such a big deal? What are the hurdles to an explainable model? In the search for clarity, are we sacrificing something somewhere? What are the trade-offs involved? So let us begin. Now, until recently, artificial intelligence algorithms have been notorious for being black boxes. That is, they have provided no way to understand their inner processes. This makes it very difficult to explain to anyone what is going on inside that model. Model evaluation metrics tell us that the model works. We are happy to hear phrases like 99% accuracy on test data. But we also need to know how and why it works. So there are actually two closely related terms here, interpretability and explainability. A machine learning algorithm's interpretability refers to how easy it is for humans to understand the processes it uses to arrive at its outcomes. It's about the extent to which cause and effect can be seen. That is, interpretability is the extent to which you are able to predict what's going to happen given a change in the input. It says if parameter A is changed to 4 instead of 2, I know how the outcome will change. Explainability of a model is our ability to understand why a model is doing what it is doing. It's about saying to the model, I know why you have predicted rainfall for Saturday. Now let us see what the trade-offs are. The classical trade-off has been accuracy versus interpretability. A model that has a simple structure such as linear regression is easy to explain. You can quickly point out the coefficients and that specifies the influence of a given factor. For example, in this model that estimates salary, the impact of years of education is about 4 times that of age. On the other hand, a complex model like a random forest may be very accurate and robust, but it can be impossible to explain how and why a particular decision was made. In general, as you add features or use more complicated models, interpretability gets more and more difficult. In a deep learning model with a lot of hidden layers and many connections, it can be impossible to even attempt an explanation. So why is it such a big deal? When using an algorithm's outcomes to make high-stakes decisions, it's important to know which features the model did and did not take into account. This can be critical when trying to analyze a decision that turned out bad. This concern is legally enforced in many industries like banking, insurance and healthcare, and it isn't hard to imagine why. The need for explainability here trumps the need for accuracy to an extent. If we can explain things to the stakeholder, they are much more likely to adopt that decision. Now, the true value of a model often lies in counterintuitive predictions. If we can't justify these, then the stakeholders are not going to accept our model. We cannot say we recommend this really bad sounding idea just because the model says so. Now, there's one more reason that models need to be interpretable, and that reason is training bias. Despite taking care, biases inherent in the training data find their way into the model. Now, this needs to be tackled. A model needs to be right, and it needs to be right for the right reasons too. So current research into this topic has brought forth some interesting approaches to this problem. There now exist several algorithms designed specifically to look into the heart of machine learning processes. LIME is one of these. LIME stands for Local Interpretable Model Agnostic Explanations. It tries to develop an approximation of the model by testing it out to see what happens when certain aspects within the model are changed through a process of experimentation. It's an implementation of an old philosophy. Let's do this and see what happens. Another approach is called deep lift. This is modeled in the rather tricky area of deep learning, and deep lift works through a form of backpropagation. It takes the output and then attempts to read the various neurons that have participated to create that output. The process helps shed light on the mechanism of the model. A similar approach to this is called layer-wise relevance propagation. This also works backwards from the output, identifying the most relevant neurons within the network until the path to the input is traced. So we have a number of strategies already in place, and researchers are busy developing more. The fact that large organizations and even governments are devoting so many resources to this problem underscores its importance. In 2018, the European Union formally introduced a right to explanation in the General Data Protection Right. And with that, we come to the conclusion of this session. Let us summarize the key takeaways. Models should be interpretable, which means that humans should be able to understand why a model is making a particular decision. If we can explain this to the stakeholder, they are much more likely to adopt that decision. Finally, understanding the process enables detection and correction of errors and biases that creep in despite our best efforts. So that's all for today. Thanks for watching.